Looking at those amazing discussions on automated reading as well as dose reduction, I would like to spend the next 7 minutes on talking about minimizing uncertainties at detection as a path to improved lung cancer outcomes. Now, I'm going to be talking about the white paper that just came out. That's why I have several co-authors. Quite obviously, Rick Avila and Claudia Henschke are not a part of GE Healthcare, but their participation in this paper was crucial. Hence, they're mentioned on this slide. First thing I would like to start is a little bit of a history. Now, in the history, CT was suggested as a tool to perform screening quite some years ago. That was still early 90s. I'm not going to, for the sake of time, read this, also because this was also pre large language model years. But nevertheless, what it was very important to say is that it was talking about radiologic specifics to characterize the findings for the follow-up that will come next. Now, where we are today is, this is the latest data I've been able to find, is 2021. In the US alone, there is 867,000 lung screening exams performed per year. So there is a very substantial data that is being acquired. But the whole idea in screening itself is also bringing the challenge of the stratification of detected pulmonary nodules. One thing that is happening is that I've been able to find quite some standards that are talking about using the volume doubling time as the key measure to decide and make the decision on the follow-up. Now, it's interesting that there are other standards that are not necessarily talking about volume doubling time, but they are still relating to the size of the nodule as one of the critical components of something that is helping to make the decision. Now, everything starts with a detection. So there is a lung nodule and the initial detection. This is where the clock is triggered and the timer starts. So the volume by itself is identified by the size and by the shape of the nodule. And the malignancy risk in what I just mentioned on the volume doubling time is actually done based on the follow-up and selected strategy on following up on the nodule. Whether it's in the green, it's in the yellow, or the red, malignancy risk increases. Let's change one more thing and look at the importance of the accuracy, because the black line is now representing the ground truth. So here is the 180 days, and here is the 360 days. And by the way, this is the real case example that was kindly provided by David Yankelevitz. But one thing that is always the matter of a question is, what if there is an error in identifying the size of the nodule? And what if this error persists for the following scans itself? If we inaccurately identify the size of the nodule, then the decision, especially for this breakout for 6 millimeter nodule, can either be 6 millimeters or 12 millimeters. And the whole, 6 months or 12 months. But the whole idea for also giving it time is because we're giving nodule time to grow so that we outgrow the error that is potentially brought by the CT. So if we're looking at this theoretical, empirical example, it can be that we overestimate the size at the beginning and we underestimate it then, and then we improperly stratify the lung nodule. So the whole idea was to avoid that, or at least to have the measurement. And I think beautifully correlates to the other discussions, for example, on automated reading, because, well, computer algorithms are going to only perform well if the data is accurate. Or how low does the dose really need to be if potentially we're inaccurate in the first place? All right, so this is the paper, and I will be happy also to share this paper. At the end, I will show the QR code. You can download it yourself. It's called Minimizing Uncertainties at Detection as a Path to Improved Lung Cancer Outcomes. We used our CT scanner, and we used it for the experiment. I will briefly talk about the experiment itself. And we also used the kindly provided Phantom by Acumetra with spheres that were representing various sizes of the pulmonary nodules. We've chosen 6 millimeter nodule because that is the threshold for decision making. Again, we can go smaller, we can go larger, but it was just the scope of the experiment that we've done. Now, this is the actual result. So one thing and important to mention first is we have started with existing guidelines or the default preset protocols, All of them were compliant with all the dose requirements and all the standards that are existing today, whether by AAPM or the KIBA. We went from standard and the standard just existing protocols, default existing protocols on the scanner, and we have also created, due to this experiment, the optimized protocol. Obviously, I'm not going to go into the details. That's why there is a QR code here, but this is what we've been able to accomplish as a result. So the volume bias, and the smaller is the better, is the standard, the default, and the optimized. And the volume precision, once again, this is counterintuitive, but volume precision, the lower it is the better. This is the starting point on the standard, this is the default, and this is the optimized. And ultimately, what we've been able to show is that switching from KIBA small lung nodule recommended based standard protocol to the optimized imaging protocol resulted in volume bias improvement of 49% and precision improvement of 53%. We have selected one scanner model by GE Healthcare, but there is no reason why other CTs or the CTs in the field can also not be improved with the same pattern that we have done with this experiment. So the key takeaways from my short report. Number one is the greater accuracy in small pulmonary nodule assessment elevates the value of CT data. And in the world of the value-based care in early detection of lung care that I touched in my previous talk, I think this is ultimately very important. CT scanners imaging protocols, I mentioned this, in despite of the selected model or the models in the field itself, have the potential for more accurate assessment and especially stepping into the field of early disease detection and especially automated reading of something that is small and off-isocentric, which is by nature pulmonary nodules. This potential should be realized, and this study is also demonstrating the way on how this can be done, and it pays off. For a sphere model, 12 to 15% error in diameter measurements, something that we started with, is 40 to 52% error in sphere's volume assessment because of the power of 3 and everything that geometry and volumetric geometry brings. So something that's been mentioned just a little bit earlier, ALARA safety principle, which is so important for lung nodule assessment, might better be complemented by AA principle, as accurate as achievable. And I think that this is ultimately bringing me to the acknowledgements. This team was also enforced by Claudia and David that kindly offered their expertise in making this white paper final. And with this, I very much thank you for your attention.